Imagine you're architecting the backend for a multi-million-dollar application. You've got millions of users generating an absolute avalanche of data every single second. At the very foundation of this entire system, sitting quietly on your servers, is a piece of software responsible for safely storing and retrieving every single byte, your database storage engine. Pick the wrong one, your application could literally crumble under the weight of its own success. The stakes are incredibly high, and today, we're looking at the two heavyweights battling for absolute dominance on the disk.
It's a fascinating question, isn't it? Why do some databases absolutely thrive under all that pressure, while others just completely collapse? You can think of a database engine a lot like a high-performance sports car. Sure, it might look fantastic sitting in the showroom, but when you put the pedal to the metal and demand massive scale, that underlying engine has to process thousands of operations without blowing a gasket. To really understand how they pull this off, we're going to have to look under the hood.
So here's our tale of the tape for this explainer. First, we'll outline the great storage engine Showdown. Then we'll explore why LSM trees dominate writes, followed by uncovering the hidden costs of compaction. After that, we'll pivot to B trees and the read advantage and reveal the power of transactional locks. Finally, we'll wrap it all up with the verdict. Section 1, the Great Storage Engine Showdown. Welcome to the explainer. Today, we are witnessing an epic clash between two entirely distinct philosophies of data management. We're not just talking about minor differences in code here. These are fundamentally different ways of thinking about how data should physically live on a hard drive. Okay, let's dive into this. On one side, we've got the established, reliable veteran, the B tree. First introduced way back in 1970, it uses what we call an update-in-place philosophy. Basically, it treats the disk as a set of fixed-size pages that can be carefully overwritten. It is the absolute gold standard in almost all relational databases. On the other side, we have the modern challenger, the LSM tree, or log-structured merge tree. This one uses an append-only philosophy, meaning it never modifies files in place, it simply writes new data right to the end of a file. This is the powerhouse engine behind massive-scale modern systems like Cassandra and Bigtable.
Section 2, why LSM trees dominate writes. Let's start by looking at that modern challenger. If your application needs to ingest a truly staggering amount of data, think a literal fire hose of sensor metrics or social media posts, you need an incredible offensive strategy. And the LSM tree definitely has one. Its entire architecture is built around taking chaotic random writes and turning them into lightning-fast sequential writes. And this brilliantly illustrates how that data actually flows. First, when a write comes in, it doesn't even go straight to the disk. It gets added to an in-memory balanced tree called a memtable. This keeps the incoming data perfectly sorted. Second, once that memtable fills up, usually after a few megabytes, it gets flushed down to the disk as a completely new, immutable file called a sorted string table, or SS table. Finally, step 3 happens quietly behind the scenes. The database periodically merges and compacts these various SSTC segments together to clean up any overwritten data. Now, the real genius of this architecture is rooted in the physical reality of our hardware. Sequential writes, where the disk just lays down data in one continuous, uninterrupted stream, are significantly faster than random writes, where the drive has to jump all over the place to find specific locations. By completely avoiding those update-in-place modifications and only appending data to sequential SS tables, the LSM tree achieves remarkably high write throughput. Honestly, it just absorbs data as fast as the disk can continuously spin or the SSD can linearly write. But raw speed isn't its only advantage. Because LSM trees are constantly rewriting their SS tables in the background to toss out old or deleted data, they can pack the surviving data incredibly efficiently. This means much lower storage overhead and almost zero fragmentation. Contrast that with a B tree, which is page-oriented. When a B tree page splits, or when a piece of data just doesn't perfectly fit, you end up as wasted disk space sitting there in partially filled, fixed-size pages. Section 3, the hidden cost of compaction. Now, let's slow things down for a second because no architecture is perfect. While the LSM tree is an absolute powerhouse for ingesting data, that performance definitely comes with a dark side. Let's look at the vulnerabilities hidden inside this append-only philosophy. The biggest vulnerability is a crucial industry concept known as write amplification.
Because the LSM tree never updates anything in place, a single piece of data is initially written to an SS table. But then, as those background processes kick in to merge and compact files to save space, that exact same piece of data might get rewritten to the disk again and again and again over the database's lifetime. Quite literally, this is why your SSD wears out so much faster under heavy LSM workloads.
As the source material points out, there's another hidden cost here too. You can think of compaction like this tireless background janitor, constantly organizing your files. But imagine that janitor deciding to turn on a super loud industrial vacuum cleaner right in the middle of your massive party. As Martin Kleppman notes, the compaction process can sometimes interfere with the performance of ongoing reads and writes. Your queries might be forced to just sit there and wait while the disk finishes an expensive compaction operation. And these aren't just abstract textbook algorithms. These have severe real-world consequences for your application. If those background processes suddenly hijack your finite disk bandwidth, your users are going to experience unpredictable latency spikes. A query that normally takes 10 milliseconds might suddenly take 500 milliseconds, just because it's stuck waiting on the disk. And even worse, if the flood of incoming writes is so high that your compaction janitors simply cannot keep up, you risk completely running out of disk space as those unmerged segments just pile up.
Section 4, B trees and the read advantage. Which brings us to the B tree counterattack. While LSM trees have been stealing the spotlight for their write speeds, the B tree has remained the undisputed, ubiquitous standard of databases since 1970 for a very good reason.
To really understand its advantage, let's walk through how a B tree finds your data. The database is chopped up into fixed-sized blocks, usually about 4 kilobytes. When you query data, you start right at the top, at the root page. You follow references based on key boundaries, kind of like alphabetical markers, down through the tree until you hit the specific leaf page containing your exact key and value. Now here's what's incredible. A typical B tree page has a branching factor of around 500. This means a tree that is just 4 levels deep can hold up to 256 terabytes of data. And you only ever have to check 4 individual pages to find any single record.
So, the crucial point is this. B trees provide consistently predictable, blazing fast performance for read-heavy workloads. Why? Because they avoid checking multiple data structures. Think about it. An LSM tree might have to check the mem table and then rummage through multiple different SS table files at various stages of compaction just to find one single record. A B tree, it just traverses its clean, neatly organized tree in a highly predictable manner every single time. Section 5. The power of transactional locks. But wait, the B tree has one final knockout punch. It possesses a secret weapon that gives it the ultimate edge when it comes to the core feature of traditional relational databases, strict transactions. Now, what's really interesting about this slide is that giant number 1. In a B tree, each key exists in exactly one place in the entire index, just one. Think about that for a second. In an LSM tree, because of that append-only nature we talked about, you might have an older version of a key sitting in an old segment, a newer version in a recent segment, and the brand newest version floating in the mem table. But in a B tree, it's updated in place. There is only ever one location. And this single location property, it is pure magic for relational databases. Because a key exists in only one single place, the database can directly attach strong transactional locks right to the tree structure itself. If you're building a banking app or an inventory system where you absolutely require strict, strong transactional semantics and isolation, this architecture makes managing those locks incredibly efficient and completely safe.
Section 6, the verdict. We've explored the high-throughput write strategies of the LSM tree and the predictable, read-optimized legacy of the B tree. It's time to synthesize this whole epic showdown and bring this abstract knowledge directly back to your daily engineering decisions. Here is our ultimate scorecard. For writes, the LSM tree is faster thanks to sequential appending, while the B tree is slower due to those random access page overwrites. But for reads, the B tree takes the win on speed and predictability, whereas the LSM tree is generally slower since it checks multiple structures. The LSM tree manages fragmentation way better, but the B tree provides much stronger, simpler locking mechanisms because, again, a key exists in only one place. Ultimately, it all comes down to the precise workload of your application. There's no magic silver bullet here. So, I'll leave you with this. When your next massive application hits a critical performance bottleneck and the data is just flooding in, which champion will you trust to protect your data? Are you going to append, or will you update in place? Keep learning, keep building, and we'll see you in the next explainer.